Welcome to Chapter 13, Radiographic Testing, or RT. In this chapter, we are going to build our understanding of radiography from the ground up. We will start with the history of X-rays and radioactivity, then move into atomic structure and isotopes, because you cannot really understand radiography without understanding what radiation is and how it interacts with matter. From there, we will examine the two radiation sources used in conventional industrial radiography, X-rays and gamma rays. We will look at how X-rays are generated, how radioactive sources produce gamma radiation, and why different sources are selected for different material thicknesses. We will then connect radiation physics to actual inspection practice. That means attenuation, image formation, the inverse square law, film, computed radiography, digital radiography, image quality, IQIs, and radiation safety. The objective is not simply to memorize terminology. A competent radiographer must understand why the image looks the way it does, why a particular exposure technique is selected, and how radiation protection principles are applied in the field. So, let's begin with where radiographic testing came from and how it developed into one of the major volumetric NDT methods. This slide gives us the roadmap for the entire chapter. Notice the logical progression. We begin with the history and definition of radiographic testing, then move backward into the fundamentals of matter and atomic structure. That sequence is important. Before we can understand why a radioactive isotope emits gamma rays, we need to understand the atom. Before we can understand image contrast, we need to understand how radiation interacts with matter. And before we can understand exposure technique, we need to understand attenuation and radiation intensity. The chapter then moves into practical radiography, X-ray tube construction, gamma-ray sources, the inverse square law, and the actual radiographic exposure process. After that, we examine the image itself, film, computed radiography, and digital radiography, followed by film processing, exposure charts, and image quality indicators. Finally, the chapter changes from teaching mode to examination mode. The mock questions are particularly useful because they identify the kinds of distinctions that are commonly tested. As you go through this course, keep one principle in mind: every practical radiographic decision ultimately comes back to radiation generation, radiation interaction, image formation, and radiation protection. To understand modern radiography, it helps to understand the sequence of discoveries that made it possible. In 1895, Wilhelm Conrad Röntgen was experimenting with cathode ray equipment when he observed an unknown penetrating radiation capable of producing fluorescence. He called it X-radiation, or X-rays, because the nature of the radiation was initially unknown. The significance for NDT is enormous. For the first time, it became possible to obtain information about the inside of an object without physically cutting it apart. Only 1 year later, in 1896, Henri Becquerel discovered natural radioactivity while investigating uranium compounds. This was a completely different source of penetrating radiation. Instead of producing radiation electrically, certain materials naturally emitted radiation from their atoms. Then, in 1898, Marie and Pierre Curie extended this work and discovered polonium and radium. These discoveries created the two fundamental paths that eventually led to industrial radiography: electrically generated X-rays and radioactive gamma sources. For examination purposes, remember the chronology: Röntgen, 1895, Becquerel, 1896, and the Curies, 1898. The discovery of radiation was only the beginning. The next challenge was producing radiation with enough energy and reliability to inspect industrial components. A major milestone came in 1913 with the development of the Coolidge high-vacuum X-ray tube. The improved tube provided a much more controllable and powerful source of X-rays. Then, in 1931, General Electric developed X-ray generators capable of reaching approximately 1 million volts. This was an important step toward industrial-scale radiography, and the technology became increasingly accepted for inspection. The Second World War accelerated the development of gamma radiography. Large-scale shipbuilding created an enormous requirement for weld inspection, while artificial radioisotopes such as cobalt-60 and iridium-192 provided practical alternatives to radium. The modern stage of this evolution is digital imaging. Computed radiography and digital radiography changed the workflow dramatically. Instead of developing physical film in a darkroom, the inspector can obtain and manipulate digital images. The important lesson is that today's radiography is the result of more than a century of development, from experimental X-rays to highly controlled industrial inspection systems. Now let's define radiographic testing properly. Radiographic testing is an NDT method that uses ionizing electromagnetic radiation, primarily X-rays or gamma rays, to produce an image representing differences within the test object. The key word here is volumetric. When we perform radiography, we are not limited to examining only the surface. Radiation passes through the component, and differences in attenuation can reveal internal features such as porosity, inclusions, voids, and certain types of weld discontinuities. There is another important characteristic: radiography produces a record. Traditionally that record was film. Today it may also be a digital image from CR or Dr. However, radiography has an important physical requirement. In conventional transmission radiography, the radiation source must be on one side of the component and the image receptor on the opposite side. That geometry is fundamental to the method. And remember the distinction between a discontinuity and a defect. Radiography may reveal a discontinuity, but whether it is acceptable or rejected depends on the applicable acceptance criteria. That distinction is critical for anyone working toward Level 2 or Level 3 responsibility. Radiography has remained important because it provides several capabilities that are extremely valuable in industrial inspection. The first major advantage is the permanent visual record. With film, you have a physical radiograph. With CR and DR, you have a digital record. That means the image can potentially be reviewed again later, subject of course to the applicable quality, storage, traceability, and digital image requirements. The second advantage is volumetric information. Radiography can reveal internal features without destroying the component. It is also applicable to a wide range of materials, although the practical suitability depends on material thickness, density, geometry, radiation energy, and the required image quality. Another advantage is that the image gives the interpreter a direct visual representation of variations in transmitted radiation. But don't confuse the presence of an image with automatic acceptance. The radiograph tells us what the technique has revealed. A qualified person must then interpret the image and apply the appropriate code or specification. Modern CR and DR systems add another advantage: digital images can be stored, transmitted, enhanced, and reviewed electronically. A professional Level 3 does not look only at the advantages of a method. We also need to understand where radiography can fail or become impractical. First, radiography can be expensive. There are radiation sources, exposure equipment, monitoring systems, trained personnel, regulatory requirements, and, depending on the technique, film and chemical processing. Geometry is another major consideration. Because the source and detector must be positioned correctly, complicated geometries can create significant technical challenges. Orientation is particularly important for planar discontinuities. A crack or lack of fusion does not automatically become visible just because it exists. Its orientation relative to the radiation beam determines the amount of contrast it creates. This is one of the most important principles in radiographic interpretation. Radiographic visibility depends on geometry. There is also the requirement for access to both sides of the component in conventional transmission radiography. And finally, there is radiation safety. Unlike many other NDT methods, radiography involves ionizing radiation capable of causing biological damage. So the method demands technical competence, procedural discipline, and strict radiation protection. Before we discuss radiation, we need to understand what radiation is interacting with. Everything around us is matter, and matter is composed of atoms. An atom contains a nucleus surrounded by electrons. The nucleus contains protons and neutrons. The proton has a positive electrical charge, while the neutron has no electrical charge. Electrons carry a negative charge and occupy regions around the nucleus. The number of protons is particularly important because it defines the element. If an atom has 6 protons, it is carbon. If it has 26 protons, it is iron. Change the number of protons and you have changed the element. Neutrons, on the other hand, influence the isotope and nuclear stability. Electrons are extremely light compared with protons and neutrons, but their interaction with radiation is central to radiography. In fact, many of the radiation interactions we will discuss later are fundamentally interactions between photons and electrons. So don't treat atomic structure as a separate theory section. It is the foundation for understanding attenuation, ionization, X-ray production, and radiation effects. Now let's look more closely at the electrons. The presentation uses the traditional shell notation K through Q. The K shell is closest to the nucleus and has the highest binding energy. Why does that matter to a radiographer? Because removing a tightly bound inner shell electron requires more energy than removing a loosely bound outer shell electron. That is why the K shell appears repeatedly throughout radiographic physics. When a K shell electron is removed, the atom is left with a vacancy. An electron from a higher shell can then fall into that vacancy. The energy difference may be released as characteristic X-ray radiation. The same basic concept appears in both X-ray production and the photoelectric effect. The outer shells, by comparison, have lower binding energies and are more easily involved in interactions such as Compton scattering. So, when you see the term K-shell, think of high binding energy, inner shell electron transitions, and characteristic radiation. This understanding will make the next sections on photoelectric absorption and X-ray production much easier to follow. This slide establishes another basic distinction: element, compound, and mixture. An element consists of atoms characterized by the same number of protons. A compound is different. Here, atoms of different elements are chemically bonded together. Water, for example, contains hydrogen and oxygen. A mixture contains different substances physically combined without forming a new chemical compound. Air is a good example. Why does this matter in an RT course? Because material composition affects radiation interaction. The atomic number, density, thickness, and composition of the material all influence attenuation. For example, two components having the same physical thickness can attenuate radiation differently if their densities or atomic compositions are different. This is one reason why exposure technique cannot simply be copied from one component to another without considering the material. From a level 3 perspective, the important point is not memorizing examples such as copper, water, or brass. It is understanding that material composition directly affects radiographic technique and image formation. Now we reach one of the most important concepts in radiation physics: isotopes. Isotopes are atoms of the same element that contain the same number of protons but different numbers of neutrons. Hydrogen gives us a simple example. Protium has 1 proton and no neutrons. Deuterium has 1 proton and 1 neutron. Tritium still has 1 proton, but now it has 2 neutrons. Notice what stays constant: the number of protons. That means all 3 are hydrogen. What changes is the mass number because the number of neutrons changes. This distinction is essential when we move into radioactive sources. Some isotopes are stable, while others are unstable. An unstable isotope can undergo radioactive decay and emit radiation. So remember this simple level 3 rule. Atomic number identifies the element. Mass number represents protons plus neutrons. If the proton number changes, you have a different element. If only the neutron number changes, you have a different isotope of the same element. A radioisotope is an isotope with an unstable nucleus that undergoes spontaneous radioactive decay. The important word here is spontaneous. Radioactive decay is not something we normally start and stop by changing temperature, pressure, or chemical conditions. The nucleus follows its own probability-based decay process. As unstable nuclei decay, radiation may be emitted in the form of alpha particles, beta particles, or gamma radiation, depending on the particular decay process. Now we introduce the concept of activity. Activity tells us how many nuclear disintegrations occur per unit time. The SI unit is the becquerel. 1 becquerel corresponds to 1 disintegration per second. The traditional unit, the curie, represents a much larger activity, 3.7 times 10 to the 10th disintegrations per second. Another important concept is specific activity. That is activity per unit mass. Why is this important in industrial radiography? Because source activity, source size, and source energy all influence practical radiographic performance. Half-life is one of the numbers you should be able to explain without hesitation. The half-life of a radioactive isotope is the time required for half of the radioactive atoms in the original population to decay. After one half-life, 50% remains. After 2 half-lives, 25% remains. After 3, 12.5% remains. The important point is that this decrease is exponential, not linear. Consider an industrial source such as iridium-192. Its half-life is approximately 75 days according to the presentation. That means the source does not simply lose an equal percentage every month. Instead, each successive half-life removes half of what remains. Cobalt-60 has a much longer half-life, approximately 5.3 years. This has practical consequences. A shorter half-life source changes activity more rapidly and therefore requires more frequent consideration of source strength. A Level 3 professional should understand half-life not just as an examination number, but as something that directly affects exposure calculations, source management, and radiographic technique. Here we need to make an important classification. The presentation identifies 5 radiation types: alpha, beta, neutron, gamma, and X-ray. The first 3 are particulate radiation. Alpha particles are positively charged and relatively massive. Beta radiation consists of high-speed electrons or positrons depending on the decay process. Neutrons have no electrical charge. Gamma rays and X-rays are different. They are electromagnetic radiation. They have no rest mass and no electrical charge. For conventional industrial radiographic testing, the 2 radiation types we are primarily concerned with are X-rays and gamma rays. But do not confuse their similarity with their origin. Gamma radiation originates from nuclear processes. X-rays are generated electrically in an X-ray tube. That distinction is extremely important. The radiation may behave similarly when interacting with matter, but the source mechanism is completely different. As we continue, we will examine each radiation type and then return specifically to gamma and X-ray radiation because these are the 2 foundations of conventional RT. Alpha radiation consists of a helium nucleus, 2 protons and 2 neutrons. That makes alpha particles relatively large and heavy compared with beta particles and electromagnetic radiation. Because of this, alpha particles have very limited penetration. They can be stopped by relatively small amounts of material. This explains an important radiation protection distinction. External alpha exposure is generally much less penetrating than gamma or X-ray exposure. However, internal contamination can be extremely hazardous because the radioactive material can enter the body through inhalation or ingestion. That means the hazard depends not only on radiation type, but also on the exposure pathway. Alpha radiation is not used for conventional industrial radiography. For an examination, remember the defining characteristics: alpha has a positive charge, is particulate, has relatively high mass, and has very low penetrating ability. But as an instructor, would also emphasize the deeper lesson: penetration and biological hazard are not the same thing. A radiation type with poor penetration externally can still be highly dangerous when radioactive material enters the body. Beta radiation is another form of particulate radiation. In beta-decay, a high-speed electron is emitted from the nucleus as part of the radioactive transformation. That is an important distinction. This is not an ordinary orbital electron being released from an atom. It is a nuclear decay product. Beta particles are much smaller and lighter than alpha particles and therefore have greater penetration. However, beta radiation is still much less penetrating than gamma radiation. It can produce skin exposure hazards, particularly at sufficient dose rates, and appropriate shielding depends on the radiation energy and the specific source. Beta radiation is not used in conventional industrial radiographic testing. For examination purposes, remember the contrast. Alpha is heavy, positively charged, and has very short range. Beta is much lighter, negatively charged in beta-decay, and has greater penetration. Gamma radiation, which we will discuss shortly, is not a particle with rest mass at all. It is electromagnetic radiation. Understanding these categories prevents many common examination mistakes. Neutron radiation is particularly interesting because neutrons have no electrical charge. That absence of charge allows them to interact with nuclei differently from charged particles. Neutrons can be highly penetrating, and conventional shielding requires materials rich in hydrogen, such as water, polyethylene, or concrete. A common mistake is to assume that because lead is an excellent shield for X-rays and gamma rays, it must automatically be the best shield for neutrons. That is not correct. Neutron interactions can also produce activation, meaning that some materials exposed to neutrons can themselves become radioactive. Neutron radiography is a specialized NDT method, but it is distinct from the conventional X-ray and gamma-ray radiography covered in this chapter. So for examination purposes, keep the identity clear. Neutron, neutral particle, high penetration, hydrogen-rich shielding, and capable of producing activation. This is one reason radiation protection must always be based on the actual radiation type and energy, not simply on the word radiation. This is one of the most important comparison slides in the entire chapter. Gamma rays and X-rays are both electromagnetic radiation. They have no electrical charge and no rest mass. The difference is their origin. Gamma rays originate from the nucleus of a radioactive atom. X-rays used in industrial radiography are generated by an electrically powered X-ray tube. Gamma sources have characteristic energies determined by the isotope. The operator cannot simply increase the gamma-ray energy by turning a control knob. An X-ray system is different. Its beam characteristics can be adjusted by changing operating parameters such as kilovoltage and current. Another major operational difference is that an X-ray machine can be switched on and off. A radioactive source continues to emit radiation while radioactive material remains active, although shielding and source storage control the exposure. This distinction is fundamental. Gamma means nuclear origin. X-ray means electronic equipment producing electromagnetic radiation. Once you understand that difference, the choice between an X-ray generator and a gamma source becomes much easier to understand. Now we arrive at the concept that connects radiation physics directly to the radiographic image, attenuation. Attenuation is the reduction in radiation intensity as radiation passes through matter. It occurs through interactions such as absorption and scattering. Several variables control attenuation. Thickness is one of the most obvious. The more material the photon must travel through, the greater the probability of interaction. Density also matters. A denser material generally presents more matter in the photon path. Atomic composition matters as well. Atomic number influences interaction probabilities. And photon energy is critical. Higher energy photons generally penetrate further and experience less attenuation than lower energy photons. Now connect this to the radiograph. Where radiation is strongly attenuated, fewer photons reach the image receptor. Where radiation is weakly attenuated, more photons reach the receptor. That difference in transmitted radiation is what ultimately produces image contrast. So when you think about radiography, think about a competition between photon transmission and photon attenuation. The radiographic image is essentially a map of those differences. Before discussing the three major photon interactions, we need to distinguish excitation from ionization. Excitation occurs when an electron absorbs energy and moves to a higher energy state but remains associated with the atom. Eventually, that electron can return to a lower energy state, releasing energy. Ionization is more significant from a radiation protection perspective. Here, sufficient energy is transferred to remove an electron completely from the atom. The atom is now positively charged because it has lost a negative electron. The released electron can then interact with other atoms and create additional ionization. In biological tissue, these interactions can produce chemically reactive species and free radicals, which can damage cellular structures including DNA. This is the fundamental reason ionizing radiation is biologically hazardous. From a radiographic perspective, remember the simple distinction. Excitation raises an electron to a higher state. Ionization removes the electron from the atom. The three photon interaction mechanisms we are about to examine are specific forms of energy transfer involving ionization and scattering. The photoelectric effect is a complete absorption process. A photon interacts with a tightly bound inner shell electron, typically a K-shell electron. If the photon has sufficient energy, the photon is completely absorbed and the electron is ejected from the atom. That ejected electron is called the photoelectron. We now have a vacancy in the K-shell. An electron from a higher shell can fall down and occupy that vacancy. The difference in binding energy can be released as characteristic radiation. This sequence is extremely important because it explains both the physics of image formation and the production of characteristic radiation. From the radiographic point of view, photoelectric absorption contributes strongly to subject contrast. For examination purposes, remember the defining feature. The incident photon is completely absorbed. That is what separates the photoelectric effect from Compton scattering, where the photon survives but changes direction and loses energy. This distinction is frequently tested because confusing absorption and scattering leads to incorrect answers about image contrast and scatter. The Compton effect is different because the incident photon is not completely absorbed. Instead, the photon interacts with an electron, transfers part of its energy to that electron, and then continues in a different direction with lower energy. That scattered photon can interact again, creating additional scattered radiation. This is a major concern in radiography because scatter can reach the image receptor from directions other than the intended primary beam. The result is loss of image quality and unwanted image fog. The slide identifies three practical manifestations of scatter that radiographers need to recognize: reflective scatter, backscatter, and edge-related effects. This is why good radiographic technique includes controlling the radiation field and considering the surroundings of the exposure. A Level 3 inspector should never think of scatter as merely a theoretical radiation physics topic. Scatter directly influences image quality, contrast, interpretation, and radiographic sensitivity. The key examination statement is simple. Compton interaction produces a scattered photon with reduced energy. Pair production becomes possible only when photon energy exceeds the required threshold. The critical number to remember is 1.02 MeV. A high-energy photon interacts in the field of the nucleus and is converted into an electron and a positron. The minimum rest mass energy required is 1.02 MeV because each particle has a rest energy of approximately 0.511 MeV. The positron does not normally remain in the material for long. When it encounters an electron, annihilation occurs. The electron and positron disappear, and their rest mass is converted into two photons, each with approximately 0.511 MeV. This is an excellent example of conservation of energy. One photon enters with at least 1.02 MeV. The resulting electron-positron pair carries the corresponding energy, and annihilation produces two photons whose combined rest energy is 1.02 MeV. For level 3 examination purposes, memorize the relationship. Pair production threshold, 1.02 MeV. Annihilation, two photons at approximately 0.511 MeV each. An X-ray tube needs three fundamental things to produce X-rays. First, we need electrons. The cathode filament is heated, causing electrons to escape from the filament surface. This process is thermionic emission. Second, those electrons need to be accelerated. A high electrical potential difference between the negative cathode and positive anode accelerates the electrons toward the target. Third, the electrons must be suddenly decelerated. That occurs when they strike the tungsten target in the anode. The fascinating part is what happens to the electron energy. The overwhelming majority of the energy becomes heat. Only a small fraction becomes useful X-ray radiation. That explains why X-ray tube design places such enormous importance on heat management. The target material, anode construction, cooling system, and operating limits all exist because the tube must survive this extreme energy conversion process. So, if you are asked how an X-ray tube produces radiation, think of the sequence. Create electrons. Accelerate electrons. Suddenly decelerate electrons. That is the basic mechanism. The cathode is the negative side of the X-ray tube and its primary role is to provide electrons. The most important component is the tungsten filament. Tungsten is selected because it can tolerate very high temperatures and provides suitable electron emission characteristics. When current passes through the filament heats up. At sufficiently high temperature, electrons acquire enough energy to escape the metal surface. This is thermionic emission. A focusing cup then helps concentrate the electron cloud toward the anode target. Now notice the relationship between filament current and X-ray quantity. Increasing Ma increases filament heating and generally increases the number of electrons available to travel toward the target. More electrons striking the target means more X-ray photons are produced. But Ma is primarily associated with quantity, not the fundamental energy of the photons. That is a critical examination distinction. If you want to change the penetrating capability of the beam, the major control is kV. If you want to change the number of photons, Ma is the important control. The anode is the positive electrode and contains the target where X-rays are generated. The target material is tungsten because tungsten has a high atomic number and can withstand extremely high temperatures. The anode also has an important thermal function because almost all of the electron energy becomes heat. The target is angled, and that geometry is related to the effective focal spot. A smaller effective focal spot can improve image sharpness because it reduces geometric unsharpness. Now consider the second major control, kilovoltage. Increasing kV increases the potential difference between cathode and anode. Electrons therefore reach the target with greater kinetic energy. That produces a higher energy X-ray beam with greater penetrating capability. So the classic level 3 distinction is: Ma primarily controls quantity. kV primarily controls energy or quality. The tube operates under high vacuum because the electrons must travel from cathode to target without being significantly obstructed by air molecules. This entire system is therefore a carefully engineered balance between electron production, acceleration, X-ray production, focal spot geometry, and heat management. There are two fundamental X-ray production mechanisms shown here. The first is Bremsstrahlung. The word comes from German terminology associated with breaking radiation. As a high-speed electron passes close to the nucleus of a target atom, its path can be deflected and its velocity can change. The lost kinetic energy can appear as an X-ray photon. Because the amount of energy lost can vary, Bremsstrahlung produces a continuous spectrum. The second mechanism is characteristic radiation. A high-energy incoming electron can eject a K-shell electron from the tungsten atom. An electron from a higher shell then falls into the vacancy. The energy difference between those shells is emitted as an X-ray photon with a characteristic energy determined by the target material. Therefore, remember the contrast. Bremsstrahlung gives us a continuous range of energies. Characteristic K-shell radiation gives us discrete energies. Both mechanisms occur inside an X-ray tube, and both contribute to the final X-ray spectrum. Now we move from X-ray generators to radioactive gamma sources. The presentation focuses on three important industrial isotopes: cobalt-60, iridium-192, and selenium-75. Cobalt-60 has the longest half-life of these three, approximately 5.3 years, and provides relatively high-energy gamma radiation suitable for thicker sections. Iridium-192 has a much shorter half-life, approximately 75 days, and is widely used for industrial weld radiography. Selenium-75 has an intermediate half-life and lower photon energies, making it useful where lower energy radiation is appropriate, particularly for thinner sections. Source selection is not simply a matter of asking which isotope is strongest. The radiographer must consider material thickness, material type, required image quality, source size, exposure geometry, access, and applicable procedure requirements. A gamma source is physically small, but its radiation field is not small. Radiation emerges from the source in many directions, so a collimator is used to direct the useful beam toward the test area. This is where radiation physics becomes field practice. The inverse square law is one of the most important calculations in radiation safety and radiographic practice. The principle is simple. As radiation travels away from a point source, the radiation spreads over an increasingly large area. Because the area increases with the square of the distance, intensity decreases with the square of distance. The formula is I1 divided by I2 equals D2 squared divided by D1 squared. The easiest relationship to remember is this. Double the distance and the intensity becomes 1/4. Triple the distance and the intensity becomes 1/9. Quadruple the distance and the intensity becomes 1/16. This is why distance is such a powerful radiation protection tool. For example, if a dose rate is 100 units at 1 foot, moving to 2 feet reduces the idealized intensity to 25 units. This is not a linear relationship. Doubling the distance does not mean reducing the dose by half. It reduces it by a factor of 4. That distinction should be automatic for anyone working in radiography. Now let's take the inverse square law out of the classroom and put it into a real radiation safety situation. During a radiographic exposure, personnel must remain outside the appropriate controlled area unless their presence is specifically authorized and protected. How do we establish a safe standoff distance? One important tool is the inverse square law. The rearranged relationship allows us to calculate the distance required to reduce a measured intensity to a desired value. The equation is D2 equals D1 multiplied by the square root of I1 divided by I2. In practical work, this calculation is only one part of the radiation protection process. We must also consider shielding, source characteristics, geometry, scatter, regulatory requirements, and actual radiation surveys. Never rely on a theoretical calculation alone when a radiation survey is required. The practical lesson is that distance provides a very powerful reduction in exposure. If you can increase your distance from the source significantly, the reduction in radiation intensity can be dramatic. This is why time, distance, and shielding form the foundation of radiation protection. Now let's connect all of the physics to the actual RT workflow. The first step is positioning the radiation source. The source must be correctly aligned with the component and the required area of interest. The second step is positioning the image receptor on the opposite side of the component. The third step is making the exposure. This is where material thickness, radiation energy, source to object distance, and exposure time come together. The fourth step depends on the image medium. Film must be chemically processed. CR requires the imaging plate to be read. DR produces the image electronically. Finally, we evaluate the radiograph. This last step is important because producing an image is not the same thing as interpreting it. The qualified interpreter must determine whether the image meets the required quality and whether relevant indications are present. Then the appropriate acceptance criteria are applied. So, regardless of whether we use film, CR, or DR, the fundamental logic remains. Position, expose, acquire, process, and evaluate. Before digital radiography became common, industrial radiography relied heavily on photographic film. Radiographic film consists of a flexible base with radiation-sensitive emulsion. The emulsion contains silver halide crystals suspended in gelatin. When radiation reaches these crystals, it produces an invisible latent image. At this stage, you cannot simply look at the film and see the radiograph. Chemical processing is required to convert the latent image into a visible image. The most important relationship to understand is photon exposure versus attenuation. Where the test object attenuates the radiation less, more photons reach the film. More radiation reaching the film produces more development of the silver halide and therefore a darker area after processing. Where attenuation is greater, fewer photons reach the film and the resulting area is lighter. That is the basic physical chain. Material attenuation transmitted radiation film response optical density. Once you understand that chain, radiographic image interpretation becomes much more logical. Film processing converts the invisible latent image into a permanent visible radiograph. There are 5 major stages. First is development. The developer converts the exposed silver halide grains into metallic silver. Second is stopping development. The purpose is to prevent the developing action from continuing uncontrollably. Third is fixing. This is a very important examination point. The fixer removes the undeveloped silver halide crystals. It does not remove the metallic silver that was produced during development. Fourth is washing. Washing removes residual processing chemicals. And fifth is drying, which prepares the film for viewing and storage. Each stage matters. Poor development can change density and contrast. Inadequate fixing can leave residual silver halide. Insufficient washing can leave chemicals that degrade the film over time. So film processing is not simply a laboratory procedure. It is part of radiographic quality control. A technically excellent exposure can still produce a poor radiograph if the film processing procedure is poorly controlled. Film selection is a balance between image quality and exposure time. A slower, fine-grained film generally provides higher image quality and finer detail, but it requires a longer exposure. A faster film reduces exposure time but generally sacrifices some image quality. Exposure charts help the radiographer select appropriate operating conditions instead of relying on repeated trial and error. Another important concept is the characteristic, or H&D, curve. It relates film density to exposure and helps describe film speed and contrast characteristics. Now we come to the image quality indicator, or IQI. The IQI is not a defect measuring device. Its purpose is to demonstrate that the radiographic technique has achieved the required sensitivity. Depending on the applicable system, the IQI may use wires or a plaque and holes. The key point is that the required IQI feature must be visible according to the governing procedure. If it is not visible, the radiographic technique may not be adequate. So remember, IQI demonstrates radiographic sensitivity. It does not directly measure discontinuity size. Computed radiography, or CR, provides a bridge between traditional film radiography and fully digital detector systems. Instead of film, CR uses a reusable photostimulable phosphor imaging plate. During exposure, the radiation creates a latent image within the phosphor material. The plate is then placed into a reader. A laser scans the plate and stimulates the trapped energy, producing emitted light. That light is detected and converted into an electrical signal. The computer processes the signal and produces a digital radiographic image. One of the major advantages is that the imaging plate can be erased and reused. This eliminates conventional darkroom processing and makes digital storage and transmission possible. The radiographer can also manipulate the digital image, for example, by adjusting display characteristics. But remember, image manipulation does not create information that was never captured. Digital processing can help display information, but it cannot replace an inadequate radiographic technique. That is a very important professional principle. Digital radiography, or DR, takes the digital concept one step further. Instead of removing an imaging plate and placing it into a reader, the DR system uses a fixed digital detector array. The detector contains many individual pixels that respond to incident radiation and produce electrical signals. Those signals are processed electronically to generate the radiographic image. The major practical advantage is speed. A DR system can provide an image very shortly after exposure, allowing the operator to evaluate the result almost immediately. There is no film processing step and no separate CR plate reader. DR also provides significant flexibility in image display and digital image processing. However, the advantages come with trade-offs. DR systems are typically expensive, detectors can be fragile, and personnel require appropriate training in digital image evaluation. A further concern is that the convenience of digital imaging can encourage unnecessary exposures if the workflow is not properly controlled. The correct approach is not to take more images simply because they are easy to acquire. The objective remains the required inspection information with the minimum necessary exposure. This comparison is important because it allows us to see the evolution of radiographic image acquisition. Film is the traditional method. It requires chemical processing, produces a physical image, and cannot be digitally adjusted after exposure in the same way as CR or Dr. CR uses a reusable phosphor plate. The exposure is similar in concept to film, but the plate must be read by a scanner before the image becomes available. DR uses a fixed electronic detector and provides the fastest image acquisition. So, when comparing the three, don't ask simply, which one is best? The correct engineering question is, which system is appropriate for the inspection requirement? We consider required image quality, productivity, access, equipment availability, cost, environmental conditions, radiation dose, digital image requirements, and applicable procedures. Film may still be appropriate in some applications because of its established characteristics and physical record. CR can provide flexibility where portability is important. DR can provide rapid feedback and digital workflow integration. The expert chooses the technique based on the inspection requirement, not simply on the newest technology. Now we move into one of the most important responsibilities in radiography, radiation safety. X-rays and gamma rays cannot be detected by our senses. You cannot see them, hear them, smell them, or feel them during exposure. That makes radiation particularly dangerous because the absence of a sensory warning does not mean the absence of a hazard. Ionizing radiation can produce changes at the cellular and molecular level. It can damage biological molecules, including DNA. The biological effect depends on factors such as radiation type, dose rate, exposure geometry, and individual circumstances. This is why industrial radiography requires formal radiation protection programs, qualified personnel, monitoring, controlled areas, and compliance with applicable regulations. A professional radiographer should never depend on intuition when dealing with radiation. Radiation protection must be engineered and verified. That means calculating where people can safely stand, using shielding where appropriate, controlling access, surveying radiation levels, and maintaining proper personal dosimetry. The basic objective is straightforward. Prevent unnecessary exposure. This slide brings together the major concepts we have developed. Radiographic testing uses ionizing electromagnetic radiation to create images representing variations within a test object. We began historically with the discovery of X-rays and radioactivity. We then established the structure of the atom, including protons, neutrons, electrons, and electron shells. From there, we moved into isotopes and radioactive decay. We classified radiation into particulate and electromagnetic forms and identified X-rays and gamma rays as the principal radiation types used in conventional RT. Then we studied the interaction mechanisms, photoelectric absorption, Compton scattering, and pair production. After that, we examined X-ray tube operation and gamma-ray source selection. The inverse square law gave us the mathematical basis for understanding how radiation intensity changes with distance. Finally, we looked at image acquisition using film, CR, and Dr. The important thing is to see these topics as one connected system rather than isolated facts. Radiation is generated, interacts with matter, is detected, and then interpreted, while radiation protection controls the hazard throughout the process. Now we begin the knowledge check section. Question 1 asks for the fundamental definition of radiographic testing. The correct concept is the use of ionizing electromagnetic radiation, X-rays or gamma rays, to produce an image for evaluation. Notice how the distractors represent other NDT methods. Ultrasonic testing uses sound waves. Magnetic particle testing uses magnetic fields. Liquid penetrant testing is primarily concerned with surface-breaking discontinuities. So the examination strategy here is to identify the defining physical principle of the method. Question 2 moves into the history of industrial radiography and asks about the development of million-volt X-ray generators. The important lesson is that radiography became an industrial inspection method because radiation generation technology progressed to energies capable of penetrating significant sections of engineering materials. When studying historical questions, don't memorize isolated names without understanding why the milestone mattered. The development of higher energy X-ray equipment expanded the practical range of industrial radiography. Question 3 tests the definition of isotopes. Remember the rule: isotopes are atoms of the same element, meaning they have the same number of protons, but they have different numbers of neutrons. Changing the neutron count changes the mass number but does not change the element identity. Question 4 tests radiation penetration. Alpha radiation has the lowest penetrating capability among the choices. The reason is related to its physical nature. An alpha particle consists of 2 protons and 2 neutrons and carries a positive charge. Its relatively large mass and charge cause strong interactions with matter, resulting in a very short range. This is a good example of why understanding the physics is better than memorizing an answer. If you remember only alpha equals paper, you can answer one question. If you understand why alpha has low penetration, you can answer many different questions about shielding, biological effects, and radiation behavior. That is the level 3 approach: understand the mechanism, then use the mechanism to derive the answer. These 2 questions focus on radiation interaction. Question 5 asks about the Compton effect. The presentation identifies the relevant energy range as approximately 0.1 to 3 MeV. More importantly, remember what actually happens. The photon interacts with an electron, transfers part of its energy, changes direction, and continues as a lower energy scattered photon. That scattered radiation can degrade radiographic image quality. Question 6 tests pair production. The critical number is 1.02 MeV. Once pair production occurs and the positron encounters an electron, annihilation produces 2 photons of approximately 0.511 MeV each. This is one of those numerical relationships that is worth knowing directly. The examination technique is to associate each interaction with its physical signature. Photoelectric, complete photon absorption. Compton, scattered lower energy photon. Pair production, electron and positron, followed by annihilation. If you know those three signatures, many radiation physics questions become straightforward. Question 7 moves to the X-ray tube. The cathode is the negative electrode, and it contains the filament responsible for thermionic electron emission. This is fundamental. If you see negative electrode, filament, or electron source, think cathode. Question 8 asks what happens when kV is increased. Increasing kV increases the potential difference across the tube. That accelerates electrons toward the target with greater kinetic energy, producing a higher energy X-ray spectrum and generally greater penetrating capability. This is why kV is associated with beam quality or energy. Do not confuse this with Ma. Increasing Ma primarily increases the number of electrons striking the target and therefore increases X-ray quantity. So for examination purposes, cathode equals electron source. Anode equals target. Ma equals quantity. kV equals energy and penetrating capability. These four relationships should be automatic before you move into advanced radiographic technique. Question 9 tests the inverse square law. If intensity is 400 units at 1 foot, moving to 2 feet reduces the idealized intensity to 1/4. 400 divided by 4 gives 100. The important point is not the arithmetic. It is understanding why the factor is 4. Distance is squared. Question 10 tests industrial gamma source selection. The presentation identifies iridium 192 as the widely used source for the indicated steel thickness range. For level 3 preparation, you should associate source selection with several variables, including photon energy, material thickness, source size, exposure geometry, and required image quality. Do not interpret an isotope table as a rigid rule that works independently of the applicable procedure. Actual radiographic technique must always follow the governing procedure and applicable code. The examination objective, however, is to recognize the characteristic applications and half-lives of the common industrial sources. Question 11 tests computed radiography. The latent image in CR is stored in the reusable phosphor imaging plate. It is not stored directly as a conventional silver halide film image, and it is not initially captured by a fixed DR detector. The plate must later be scanned by the CR reader. Question 12 tests film processing. The fixer removes the undeveloped silver halide crystals. This is a classic examination trap. Development converts exposed silver halide into metallic silver. Fixing removes the remaining undeveloped silver halide. Therefore, if you remember only one sentence from this question, remember. Developer creates the visible silver image, fixer removes the unused silver halide. This distinction is important not only for examination questions but also for troubleshooting poor film processing. If the chemistry is incorrectly controlled, the final film density, contrast, clarity, and archival quality can all be affected. Question 13 returns to X-ray production. Bremsstrahlung produces a continuous range of photon energies. The maximum photon energy is related to the accelerating voltage applied to the X-ray tube. That is why Bremsstrahlung should immediately suggest the phrase continuous spectrum. Question 14 asks about half-life among the listed industrial sources. Cobalt-60 has a much longer half-life than iridium-192 and selenium-75. The practical significance is important. A long half-life means the source activity decreases more slowly over time. A shorter half-life means the source strength changes more rapidly. This directly affects exposure planning and source management. For examination preparation, memorize the characteristic values presented in this course, but also understand what those values mean operationally. A number becomes much easier to remember when it is connected to a physical consequence. Question 15 tests the photoelectric effect. The key feature is complete absorption of the incident photon. A K-shell electron is ejected, creating a vacancy, and an outer shell electron can then move inward and emit characteristic radiation. That is the physical sequence you should visualize. Question 16 compares DR with CR. The major operational advantage of DR is rapid image availability. There is no separate plate reading step. The detector sends electrical information directly into the digital imaging system. But remember the engineering trade-off. Higher speed does not automatically mean better inspection. A DR system still requires correct exposure, appropriate detector positioning, image quality control, calibration, and competent interpretation. The technology changes the acquisition process, but it does not eliminate the fundamental principles of radiography. You still need adequate radiation transmission, appropriate contrast, geometric control, scatter control, and sufficient image quality. Technology changes the workflow, not the underlying physics. Question 17 asks about gamma emission. Gamma emission changes the energy state of the nucleus without changing the number of protons or neutrons. That is an important distinction from alpha and beta decay. Alpha emission changes the nuclear composition by removing 2 protons and 2 neutrons. Beta decay changes the proton-neutron relationship. Gamma emission, by contrast, is essentially the nucleus releasing excess energy. Question 18 tests specific activity. Specific activity means radioactive activity per unit mass. This is particularly relevant for understanding why a small physical source can have a very high radiation output. Source dimensions matter greatly in industrial radiography because source size influences geometric sharpness, while activity influences exposure capability. That means a radiographic source is not described adequately by activity alone. The radiographer needs to understand both the radiation output and the physical source geometry. That relationship becomes especially important when optimizing image quality. The final 2 questions test scatter and film selection. Question 19 concerns backscatter. Backscatter comes from radiation that has scattered from objects behind the image receptor and returned toward the imaging medium. This is one reason radiographic setups must consider the environment around the exposure, not just the component itself. Question 20 asks which film provides the highest quality radiograph. The presentation identifies slow, fine-grained film. The reason is that fine-grained film provides better detail and resolution, although the trade-off is longer exposure time. This is an important general engineering principle. Performance improvements often involve trade-offs. A faster film may improve productivity but sacrifice some image quality. A slower film may provide better detail but require more exposure time. The correct choice depends on the inspection requirement. For examination questions, however, remember the relationship presented here. Slow and fine-grained equals highest film image quality. This is the major revision slide, so let's connect everything one final time. Radiographic testing is a volumetric NDT method using ionizing electromagnetic radiation. The history begins with the discovery of X-rays and natural radioactivity and progresses through the development of industrial X-ray equipment and artificial radioactive sources. The atom gives us the foundation for understanding radiation. Isotopes have the same number of protons but different numbers of neutrons. Radioisotopes undergo spontaneous radioactive decay. For conventional RT, the key radiation types are X-rays and gamma rays. X-rays come from an electrically powered tube. Gamma rays come from radioactive nuclei. Radiation interacts with matter through mechanisms such as photoelectric absorption, Compton scattering, and pair production. The X-ray tube uses a cathode to generate electrons and an anode target to convert electron energy into X-rays. Ma is primarily associated with quantity, while kV is associated with beam energy. Then we use film, CR, or DR to capture the transmitted radiation. And throughout the entire process, radiation protection remains essential. This is the conceptual framework you should carry into every RT examination and every practical inspection. This slide is your numerical revision sheet. These are the numbers that should become familiar enough that you do not have to reconstruct them from memory during an examination. First, activity is measured in becquerels, where 1 becquerel equals 1 nuclear disintegration per second. The traditional Curie is 3.7 times 10 to the 10th disintegrations per second. Then we have the inverse square law. Remember the relationship between intensity and distance. If distance increases, intensity decreases according to the square of that distance ratio. Next are the radiation interaction ranges presented in this chapter. The photoelectric effect is associated with lower photon energies. Compton scattering occupies an intermediate energy range. Pair production requires a threshold above 1.02 MeV. And then we have the source half-lives. Cobalt, 60, approximately 5.3 years. Iridium, 192, approximately 75 days. Selenium, 75, approximately 120 days. Do not simply memorize these numbers individually. Build associations. 1.02 MeV, pair production threshold. 0.511 MeV, annihilation photon. Inverse square, distance squared. Co, 60, long half-life. IR, 192, widely used industrial gamma source. That makes the information much easier to retain. We have reached the end of chapter 13. But completing the presentation does not necessarily mean mastering the subject. Use this final checklist as a self-assessment. Can you define radiographic testing and explain why it is considered a volumetric method? Can you explain the historical development of X-rays, radioactivity, and industrial radiography? Can you describe the atom, including protons, neutrons, electrons, and electron shells? Can you distinguish alpha, beta, neutron, gamma, and X-ray radiation? Can you explain the 3 major photon interaction mechanisms? Can you explain how an X-ray tube produces radiation, including the roles of the cathode, anode, filament, target, kV, and Ma? Can you explain the major industrial gamma sources and their half-lives? Can you perform an inverse square calculation? Can you explain film, CR, and DR image formation? Can you explain every step of film processing? And finally, can you explain radiation protection using the principles of time, distance, and shielding? If you can answer those questions without relying on the slide, you are moving from memorization toward genuine RT competence. The objective of Level 3 knowledge is not simply to recognize the correct answer. It is to understand why the answer is correct, when the principle applies, what its limitations are, and what can go wrong in the field. That is the mindset you should carry forward into the next chapter of your NDT training.